Thank Vero for introducing the real-world recommendation problems. So I will continue the discussion. After formulating the real-world recommendation problems, I will abstract the problem and look at the theory behind it. We'll talk about how to link Bayesian optimization to this problem. We need to modify the Bayesian optimization and apply some tricks. In terms of the acquisition function in Bayesian optimization, we use the Thompson sampling, and I'll specify the reasoning. We'll also introduce Thompson sampling in more detail in this section. Here we use Y to represent a matrix, and X represents a hyperparameter to tune. The major matrix is Y of X. This is the main objective we want to optimize. Besides the major matrix, we may have many guardrail matrices YKX. This is generally happens when we launch a new model online. We need to conduct an A/B test to compare the performance of the new model and the control model over many metrics. There is one major metric, but there are also many guardrail metrics. The new model should outperform the control model in terms of the major metric as well as all of the guardrail metrics. We need to tune hyperparameters to optimize the major metric while making sure that the guardrail metric do not drop below the threshold CK. So this is a constraint optimization problem. However, we can easily see that there's one challenge. So because that we don't know the form of the yx, y1x, y2x up to the ykx. It can be any nonlinear function. Therefore, we cannot use the linear programming, quadratic programming, or the convex optimization methods. Moreover, the metrics are often noisy, so that we need to use a robust and reliable estimation methods. The procedure we perform is that we first estimate y of x and all the guardrail metrics, and then use the estimated function as a surrogate function to perform the optimization. So in the first step, we apply the Gaussian process to estimate the metrics. And in the second step, we use the estimated Gaussian process curves as a surrogate function and to apply the method of Lagrange multipliers as well as Thompson sampling, which we'll introduce in the later slide. Let's first talk about the first step. How do we estimate the metrics? I listed some examples that Y1 can be to help you understand. Yx can be a member viral actions in feed and invitation rate in POMK. And Yk of x can be the job application metrics in feed as well as the application acceptance rate in POMK. We can use a different distribution of Yx to given the different nature of the metrics. For example, we can use Gaussian distribution. In this case, we have a noise parameter to estimate, and we can also supply the pre-specified the noise information. And we can also use binomial distribution to model integer metrics. Here, y of x is an integer success count metric, and nx is a total count. Yx followed binomial distribution with nx and the success rate. The success rate has a sigmoid link to the underlying the Gaussian process. We can also use a Poisson distribution to model integer metrics. Here, the yx is the count metric and the nx is a normalizer. The data is linked through the Gaussian process via a log link. After estimating all the metrics via Gaussian process, we need to solve the constraint optimization problem. The yx are samples from the Gaussian process so that there's no closed form. We need to use the method of Lagrange multipliers. So we construct a new function L of x, which is equal to the yx and plus the k constraint components as here is lambda 1 times the sigma alpha of the y1x minus c1 and up to the k. So the sigma of a is a smoothing sigmoid function, which takes form of the inverse of the 1 plus e to the power of minus alpha z. Here, the alpha is a large value, and the sigma alpha takes a value close to 1 when for positive z and close to 0 for the negative z. So sigma alpha is actually a smoothing function for the stepwise function. So if we look at the form of the function, and we can know that for the case satisfied, if the constraint is satisfied, which is y1x is larger than c1, so the whole term is close to the lambda 1. If the y1x is smaller than c1, the whole form is close to 0, which means that this kind of a function we can help us identify how many constraints are satisfied and how many constraints are violated. In real applications, we choose a large lambda k to guarantee that all constraints are satisfied. We can also tune the lambda k to adjust the strictness of the constraints. Through the Lagrangian multiplier, we can combine all the functions into the Lx, and thus this is a single objective. Through the optimizing of the Lx, we can guarantee that we maximize Yx, as well as we can guarantee that all the constraints are satisfied. Recall that after fitting the Gaussian process, we can generate posterior samples of Yx and Ykx. Therefore, we can generate samples from Lx. In this way, we combine the Lagrangian multipliers and the GP to solve the nonlinear optimization problems. The next step is to obtain the optimal value from Lx. So this also falls into the routine, the Bayesian optimization region. We first maximize a single function, Lx. In order to do this, we connect the training data, and we can generate the posterior samples, and we can apply some of the acquisition functions. But there are some tricks we'll see that to make this work. The first trick is about the connecting the matrix and obtaining the posterior samples. The traffic is often limited for online hyperparameter tuning and A/B test. We cannot connect the matrix on every point. So one efficient allocation method is to use equal-spaced Sobel points. Sobel points offer a low discrepancy than the same number of the random points. So we can see from the figure below, so the points from the left side is purely drawn randomly. The points from the right side comes from the Sobel generator. We can easily see that the Sobel generator has a better coverage, but randomly drawn points contain a large low coverage region. Besides, we can construct Sobel points in any dimension, especially in the high dimension, so Sobel points does not suffer from the curse of dimensionality. And for every sequence of the Sobel points, they are equal spaced. The second trick is about how do we reweight the points. After initially collecting the matrix and serving those points equally in the recommender system, finally we can get the training data, for example, after several hours or after 1 day. So we can fit the Gaussian process over the data, and we can generate samples from L of x. We can then generate one sample from Lx and obtain the maximum. This method is simple, but it's too greedy since we haven't explored a lot. We can also, for example, use the EI, expected improvement, or the UCB, upper confidence bound, or other acquisition functions. But those functions does not take online serving nature into consideration. Remember, for each candidate point is associated with the traffic volume served, which can be described as a probability value P of I. So if there is one acquisition function which could output the probability, which is proportional to the likelihood of each point being optimal, we can directly change the traffic. So this is our design choice. Instead of serving one point of all traffic, we serve many points of unequal traffic and let the algorithm converge to the best point. So here is a detailed algorithm. So the algorithm is called the Thompson sampling, which is an older algorithm proposed in 1930s, but it's still a powerful algorithm. So let's go through the step by step. So we use Thompson sampling to find the pi to each point of the xi. So the first step is that for all the candidate points, x1 up to xn, they are suitable points. We first obtain the posterior samples from the L of x. So I put a hat here, the L hat 1, x1, L hat x2, up to the L hat xn. So they are n real numbers. And the step 2 that we find the maximizer inside these endpoints. We pick xi star such that the L hat xi star is the largest among all the points. And the third step is that we need to repeat this two steps many times. For instance, repeat them 1,000 times. After 1,000 times, we can get the 1,000 points, x1 star, x2 star, and x1,000 star. So all of these 1,000 points, actually, they are points drawn from this x1 up to the xn. So that we can get the summary statistics. For example, we can count that how many times xi is in the 1,000 points. We use pi as a frequency of the xi is in the xy star up to the x1,000 star. So this is an illustration of the whole algorithm. The idea is that we need to compute the probability that each of the xi being the optimal, because this probability does not have closed form, so we can use sampling here. The sampling is a Monte Carlo sampling, so we can approximate the probability by the frequency. So in the next slide, we also have some illustration and the intuition of the Thompson sampling. So Thompson sampling is often used to select the best hyperparameters via sampling from a distribution, x1, x1, p1, x2, p2, up to the xn, pn among all the candidates. So instead of, it's not like the EI or the UCB, Thompson sampling will output a distribution. So indexed by the x1, xi, x1, p1 up to the xn, pn. And the pi is equal to the probability of each candidate being the optimal among the all. So this probability may not have the analytic solution, but that's fine. We can use the Monte Carlo sampling to approximate it. And Thompson sampling, also we have some theoretical analysis. It is proved to converge to the optimum value in various settings. And in applications, in a lot of real applications, for example, in the online A/B test, online advertising, Thompson sampling is widely used. In the final slide of this section, I want to emphasize two concepts in the hyperparameter tuning, which is exploration versus exploitation. The exploration means that we explore the suboptimal but high potential regions in the search space. Exploitation means that we search around the current optimal candidate. Actually, a lot of acquisition function balances the exploitation and the exploration, such as EI, UCB. Also, for the Thompson sampling, we can use Thompson sampling to automatically balancing the exploration and the exploitation. These two concepts are also very common in the multi-banded settings as well as reinforcement learning. So this ends a section of that how do we formulate a real-world problem and how do we use mathematics to solve this problem. Thank you, and any question is welcome.